Hello everyone. Thank you for joining this session. My name is Tomasz Zawadzki, and together with Konrad Sztyber, we'd like to share with you how to simplify your host software with IPUs. And please enjoy some notices and disclaimers. So let me first briefly describe what an infrastructure processing unit, in short IPU, actually is. So this is a new class of a device that is replacement for a standard network interface card, NIC. Uh, on the left is a simplified diagram of one example of such type of a device. Here in particular, it's Intel IPU ES2000. The exceptional part is that it contains a generic purpose processing power as well as hardware accelerators. In other terms, it is a PCIe card inserted into the host that presents different types of devices to the host, such as network card or NVMe device. So this provides a clear separation between the host and infrastructure. Yet another benefit are dynamic changes of what functionality is presented to the host, as well as what kind of features. So this presentation will focus on storage use cases for IPU and how SPDK is an ideal candidate for software that runs on IPUs. Let me describe in this section what specific storage features are key for IPU and how does managing storage work there. So drilling into details of what is different between using standard NIC and IPU in regards to software running on each. We'll be focusing on NVMe here. So in deployments that do use NICs, the software stack on the host need to run NVMe driver that serves as NVMe over Fabric's initiator. That by itself consumes non-trivial amount of CPU, especially during performance-intensive periods. Additionally, the host needs to support any required features for NVMe-oF. It applies to Linux kernel, Windows, or user space software stack. And obviously, the support for those features differs between all of them. Meanwhile, when storage management is moved to the IPU, the software required is only limited to NVMe PCI driver, which is much thinner layer. NVMe-oF initiator is moved down to the IPU, freeing up CPU cycles on the host. The host itself can treat the NVMe device presented from IPU the same as any other locally attached NVMe device. So taking the prior slide at face value, it might not seem like a big deal, but let's discuss how the same problem looks at the data center scale and what problems there can be with managing such infrastructure. So configuring a single host versus multiple is vastly different. This is simply a problem of scale, especially when comparing the easiness of loading an NVMe PCI driver to configuring NVMe-oF initiator on multiple hosts with possibly different operating systems. So the next key point is separation of software running on host and infrastructure. It drives a clear divide of responsibilities and resources. Finally, IPUs allow for changing new features like acceleration in runtime without changes in software or hardware. So going back to the issue of scale, doing all of that and doing it dynamically across the whole data center sounds great. Well, at least it does to me. So let me describe what storage management capabilities can be easily made available on IPUs utilizing SPDK storage applications. So first, the backends used to connect to remote target are interchangeable. I've already touched on NVMe-oF, but this includes iSCSI and more. So the type of backend is transparent from host point of view. The storage application itself can be configured and customized to suit required use case. Without changes to the hardware, different devices can be presented to the host. So far, we've been discussing NVMe device, but similar can be done with virtual block type device. And finally, the NVMe over Fabrics multipath and discovery are fully handled within IPU, possibly granting those kind of capabilities regardless of the host system. So besides making storage device available to the host, there are multiple storage features that can add more capabilities. For example, the common BDEF layer allows for providing quality of service control for each device. The devices presented to the host do not need to map one-to-one to those on remote NVMe-oF target. Instead, those could be split up using logical volumes or offer additional functionality like crypto, compress, caching, and many others. Think of it as adding another capability on top. Of course, new BDEFs modules are added all the time, and it is possible to use an out-of-tree BDEF module too, with whatever secret sauce that makes sense for those deploying it. So the composable nature of SPDK libraries and modules suits IPU perfectly. No better way to demonstrate that than the accelerator framework. It is used to offload operations like crypto, CRC calculations, or compression from BDEFs, target, and initiator. The interesting part happens when multiple operations are used within a single I/O. This case will be described more in depth by Konrad. So now let's get to the fun part. SPDK had support for NVMe-oF for quite a while. The part that is novel in context of IPU is how to present NVMe device to the host from an IPU, no matter what kind of device it actually is backed by. So quite a while ago, the NVMe 2.0 spec recognized the PCIe as just another transport alongside TCP, RDMA, or fiber channel. This basically follows the organization of components done in implementations like Linux kernel or SPDK. The interesting part happens when the two observations are made. So first, SPDK NVMe target already fully emulates NVMe device based on any type of SPDK BDEF. Another is that the transports are pluggable, allowing for addition of new ones. Combining those two allows to present any type of BDEF to the NVMe PCI driver on the host. So another interesting angle to take on the split between different transports is to take a look at the code breakdown between common parts for the transport handling and each particular transport. Having common part such a large part gives a consistent support for the features for all the transports. It also lowers the barrier of entry for new transport, which is evident by taking a look at the 2600 lines of code of VFIO user, a memory-based transport. So now, let me hand off to Konrad to describe how implementing IPU-specific transport can look like and the challenges that come with it.
Thank you, Tomek. Let's see how an IPU transport looks like. And let's pick a concrete example and take a look at the transport on one of the IPUs, specifically the Intel ES2000 that Tomek has already mentioned. The transport there is called NPI. This stands for NVMe Protocol Interface, and it plugs right into the NVMe transport abstraction and presents a number of PCIe NVMe devices to the host. NPI transport is responsible for providing the glue between IPU hardware, its components, and the SPDK libraries. And it's around 7K lines of code. So let's have another quick look at the code breakdown again. So as you can see, NPI is a tad bigger than other transport, but still the vast majority of the work is being done in the common layer. But before we go any further, I would like to have a quick reminder on how a transport is registered and what operations it needs to actually implement. So the key structure here is SPDK NVMe transport ops. It defines all of the interfaces that will be called by the common layer to perform some transport-specific operations. The transport, on the other hand, notifies the common layer about new requests or new connections using functions like NVMe target new Cooper or NVMe request exec. Some of these transport callbacks are required to be implemented by each transport. So, for instance, it doesn't make sense to have a transport that does not support listening on a given address or does not support creating a poll group. It's just, you cannot have that. It doesn't make sense. On the other hand, some of them are optional. For instance, not every transport requires to be notified whenever a namespace is added or removed to a subsystem. Over the years, this has proven to be a very good abstraction, but it was originally implemented with fabrics transports in mind, such as TCP, which means that there are a few caveats that you have to keep in mind when working with non-fabrics transport, such as those found on IPUs. For instance, because the host sees a PCIe device, there is no fabrics connect command. However, the common layer, the common NVMe layer, still expects it. So what we can do is whenever an IPU transport sees that a host wants to connect, for example, it can detect that by seeing that the host driver sets the enable bit in the controller configuration register. So whenever the transport sees that, it can simply send a fake connect command to the common layer to make sure it proceeds with all of those necessary NVMe device initialization. Another challenge comes with the way registers are accessed. Again, the host sees a PCIe device, so it's doing read-write operations to a PCIe bar, and it doesn't use the fabrics property get, property set commands that the NVMe layer expects. But similarly to the problem with the connect command, the transport can prepare and send a fake fabrics property get or property set command to the NVMe layer to make sure that it handles the register read or write appropriately. Then there's the issue with reporting features in the identify controller command. So fabric transport are required to support SGLs, but an IPU doesn't have to do that. So it's not a fabric transport after all, it's PCIe. So it might only support PRPs. But again, we have a simple solution here. There's a callback called cDataInit. That's called whenever a controller is created, and the transport is free to fill all of those features it actually supports in the identified controller response that will be then returned to the host whenever it queries for that identify features command. Of course, there are small issues like that, but it was relatively easy to work around all of them, which I think should prove that these abstractions works well for non-fabrics transport too. And finally, I think it's worth noting that similar challenges are also often encountered not only in IPU transport, but in other memory-based transport, such as, for example, VFIU user. So another important topic when talking about IPUs is how the data is transferred and how the operations are offloaded by the IPU hardware. So IPUs will often have hardware engines that allow for offloading some operations, such as DMA, CRC calculation, compression, or crypto to the hardware. And in SPDK, we already have abstraction for this. Tomek already mentioned it. It's called acceleration framework. It defines a plugin model, which is fairly similar to NVMe transport that can be used to implement a module for a given IPU. Of course, different types of hardware have different capabilities and might not support all of the operations. In that case, a software fallback is going to be used. But there's another challenge here. So the hardware can often perform many operations at the same time. Like you can do DMA and encryption in one go. However, those operations are often performed in completely different layers of the software stack. For instance, the NVMe transport might DMA the data from the host, while BDEV crypto might be doing the encryption. This is where the concept of operation chaining comes into the picture. The goal is to execute several operations submitted by different software modules in one go. One key observation here is that oftentimes these software modules don't really need to wait until an operation completes. For example, crypto BDEV doesn't touch the data once it's encrypted. It only cares whether the encryption was successful or not. And if it was, it pushes the request down the stack. And we can use that fact. When we want to execute an operation, we only append it to a sequence of operations and push that sequence object down the stack. We are not executing any of those operations at this point. Then, once we actually reach the bottom of the stack, when we need to move the data either over the network or to a disk, we can execute all of those pending operations all at the same time. So that way, if the hardware supports executing some of those operations as a single operation, it can be easily done at this level. Of course, this means that multiple software level layers need to be aware of this. So the acceleration framework is obviously one of them, but it's also need to be supported in the BDEF layer, in the individual BDEF modules, such as crypto or compression, the NVMe-oF target, etc. And one final disclaimer here, this is still very much work in progress. You won't find any of this on the repository just yet, but you can certainly expect it in the very near future. Now, let's change the direction a little bit and talk about orchestration. So if an IPU has a transport that's plugged into the NVMe-oF transport abstraction, not only will it reuse a lot of existing code doing the NVMe device emulation, but it will also use the same set of RPCs, like create transport, create subsystem, add listener, add namespace, stuff like that. Also, the initiator part is often covered by our regular BDEF NVMe RPCs like BDEF NVMe attach controller or BDEF NVMe start discovery. However, some of those RPCs might have IPU-specific options. For instance, when creating a transport, you might want to set some parameters that are specific to the type of hardware that you are running on. When you add a listener, the listener address might be specific to a given IPU. And this JSON-RPC interface is intentionally very low level. Its principle is to allow the user to control each and every knob that the software allows user to turn. This gives you a lot of flexibility, but also adds some complexity. So all of that means that when you want to connect a host to its backend storage, you will need to send several JSON RPCs. And each of those can fail. So you also need to handle error cases and do the appropriate cleanup. And for most orchestrators, this is all unnecessarily complex. All they want to do is to specify an address or a way to connect to some remote storage. And the block device from that storage target that they want to attach to a given host. And our answer to this problem is storage management agent, or SMA in short. It's a gRPC service running on an IPU that is responsible for managing SPDK application. Its goal is to be easily adopted by existing orchestrators, such as Kubernetes. It hides the low-level details of an IPU that is exposed in the JSON-RPC interface. And it does so by providing a very simple interface. Currently, it just consists of 6 methods that will still allow the user to attach a remote volume to the host and set up various properties such as encryption or quality of service. Currently, the interface supports creating NVMe, NVMe-oF, and virtual block type of devices. Before we dive deeper into the details, let's discuss some of the SMA's main concepts. So the first and the most important abstraction is the device. So this is an object that can expose block devices, which are called volumes, to the host using a given protocol, such as NVMe or virtual block. So in NVMe terms, a device is equivalent to an NVMe controller. Then we have a volume. This is a block device that's exposed to the host through a device. So in NVMe terms, this would be an NVMe namespace. It's important to note that a volume is always attached to a device. You can't have a volume without a device. This is because there's no separate connect step. Connecting a remote volume and then attaching it to the host through a device is always performed as a single atomic operation. And finally, there's the device manager abstraction. It isn't exposed in the API, but it is a concept in the code. It represents an object that is responsible for providing support for a given protocol using a given transport. So let's pick NVMe, for example. So an IPU and a VFIO user might both provide a way to create NVMe devices, but they do that in totally different way. So you would have two different device managers, one for VFIO user and the other one for IPU. So now that we know the basics, let's take a look at one of the RPCs exposed by SMA. Of course, this is all a little simplified, but hopefully should be enough to demonstrate the idea. So first, during the boot up, SMA will initialize the application based on some startup configuration. This will usually include stuff like creating the appropriate transport, things like that. Of course, this is not a part. This is not a part of the create device RPC, but this, I think it's important to know that this happens at the very beginning before any RPCs are actually sent. So after that happens, the user can send a create device request. We should also mention that this create device RPC is idempotent, meaning that you can send multiple requests and it will result in creating a single device, provided all of those requests are using the same parameters. So after SMA receives the create device RPC, it will create a subsystem, NVMe subsystem, of course, if it doesn't exist already. And then it will add a listener to that subsystem with some IPU-specific address that can be directly translated to a BDF that identifies a PCA device on the host side. Once that is done, an NVMe controller will appear on the host side. Of course, it will not have any namespaces yet, but it will be visible. This is pretty simple. Create device is a pretty simple command. So let's take a look at something more complicated and see how to add volumes to that device using NVMe discovery service. So as I've mentioned earlier, this consists of two steps. First, connecting to the remote storage that actually presents the volume, and then attaching that volume to a device, exposing it to the host. And similarly to create device, attach volume is also idempotent. So when a user sends this attach volume RPC, SMA will request the SPDK application to connect to a discovery service, provided it's not connected to it already. It's worth noting here that SMA keeps track of the connections to discovery services. That's because you can have multiple volumes using the same discovery service parameters, and you need to know when it's safe to disconnect from one of those discovery services. Of course, that happens when none of the volumes are attached. So after that happens, SPDK application will connect to the discovery subsystem, read all of its log pages, and then connect to the listed targets in those log pages. After that, SMA will verify that the volume requested by the user has actually been connected and is available as an NVMe BDEF. Then, if the user requested encryption to be enabled in the attached volume parameters, SMA will create a crypto BDEF on top of that NVMe BDEF. And finally, it will expose the volume to the host by adding the appropriate BDEF, either NVMe or crypto, to a subsystem that is associated with a given device. After this, the host will see a new namespace appear on the NVMe controller associated with that device. Finally, let's see how to actually implement support for an IPU in SMA. So the first thing that needs to be done is to create a plugin with a class that derives from device manager. And that class needs to implement all of the necessary methods that are defined by the device manager interface. And all of those methods directly correspond to the gRPC interface that's exposed by SMA. It's worth noting here that only one device manager can implement a given protocol at the same time. That means that if you have an IPU device manager that is capable of creating NVMe devices, you cannot use that with VFIU user, which also creates NVMe device. So after you have your IPU specific device manager, all that needs to be done is to specify the plugin and the device manager in SMA's configuration. And that, at this point, that device manager will handle all requests for the protocol that this manager supports. So this gives everyone a simple way to implement their own plugin for their IPU, even if it's out of tree. So that would be all from my side. Back to you, Tomek.
Thank you, Konrad. So let's sum up. So if there are few things we would like you to walk away from this presentation with, those would be that moving handling storage management and storage features from the host to IPU simplifies deployment of the hosts, allowing for flexibility while keeping performance in evolving data center. Another is that SPDK NVMe over Fabrics target serves as an ideal NVMe device emulation for IPUs. And finally, the composable nature of SPDK libraries and modules make it match up with goals of IPUs. We'd like to highlight one improvement that is coming in the short term, the addition of the operation chaining to SPDK acceleration framework. Besides that, there are a lot of exciting changes in SPDK to help with IPU use cases. Thank you everyone for attending this session. Please join us at spdk.io. We would love to hear your feedback.